Hi, this is Luke D, and this is De.Bio.1.2013, molecular bio thought, and today we're going to be talking about the phosphate group. So I'm on a train right now, so I apologize for that, but I just didn't want you guys to miss anything. So here's one of the last functional groups we're going to talk about. It's the phosphate group, and unlike the other groups that I talked about, I haven't put the phosphate group attached to anything. And that's because the phosphate group can really be attached to anything. You're going to see it attached to sugars, you're going to see it attached to lipids, proteins, all kinds of things all over the place. But the one thing you do have to know about it is that it's really, really negatively charged. So if you look here, you've got a negative here and a negative here. And unlike the amino acid, you're not going to have dissociation problems where, remember when we talked about the amino acid and we talked about the carboxyl group, if there was a whole bunch of, if there's a high concentration of H plus ions around, you weren't going to get the H to come off the carboxyl group. Well, the H's are almost always going to come off this phosphate group, so it's almost always going to be negative. And one thing to keep in mind, and we'll explain how this works later, is that if you have two things and they're negatively charged and you try to put them together, you're going to have to push them, right? So you're going to have to actually apply a lot of energy to get them together. So once they're together, if you let them go, they're going to fly apart. So when two negative things are together, they actually have a lot of potential energy. And this is kind of like our concentration gradient, but even more so. So if I have a high concentration of negative ions in one place, the potential energy there is actually higher than just a high concentration of regular atoms in one group. So if you imagine, you have a bunch of tennis balls in one area, and then you start shaking up that area, they're going to hit each other and they're going to all try to get out of that one area. Now imagine you have a whole bunch of magnets, but they're all north poles, and you put them in the same area. Well, they're not only going to bounce against each other, but they're also going to push against each other. So it's going to be harder to get those repelling forces all together. I hope that made sense. Let's take a look at kind of what this does. So this is a GC base pair. So there's two molecules here. You've got one nucleotide here and one nucleotide here. The phosphate group is green here, but you can also see it in orange in other models. So let's go ahead and change that to ball and stick, because I know most of us like that one a little bit better. I do as well. And zoom in just a little bit, and then we're going to start this. Okay, so you should see something interesting if we drop the temperature just a little bit right now. So you see they're pretty much just bouncing over each other, so they're overcoming any attractive forces that they might have right now. Oh, that stinks. I can't put the hydrogen bonds on. Alright, now I don't know if I can get these guys to do it, because it's kind of random when it happens. But if you look, the phosphate groups are actually on the opposite sides of the box. They'll push each other away. And then you'll have these nitrogenous base kind of ending up in the middle, kind of pointing towards each other, because they actually have parts that are attracted to each other. So for example, this hydrogen is positive, that nitrogen is negative, they're going to attract to each other. But that's why you see this conformation all the time. Let me see if I can find it. Alright, so that's why you see this conformation, where the phosphate groups are always on the other side when you have two base pairs next to each other. Now, we said that the phosphate groups were negatively charged, so they're going to be basically a way to give a molecule energy. So if we have, for example, this molecule, and if we just look at one side, so we're just looking at this right molecule here. Okay, so this one on top. You can see there's one phosphate group right here, and there's one molecule. Now, if we took that molecule and we added two more phosphate groups to it, so let's see what that would look like. Alright, so now we've added 2 more phosphate groups there. Now these are each negatively charged, so imagine how hard it is to put those together. It's going to be really, really hard. And this molecule is going to be a really, really high energy molecule. So this is a nucleic acid. And one thing you're going to notice about nucleic acids is that they have the carbon and nitrogen rings, but they also have a ring in the middle. See this guy right here? The carbon and oxygen ring? That's going to be a 5 carbon or 5 sugar ring, so 1, 2, 3, 4, 5. And you're going to see some hydroxyl groups there. Now we're going to come back to that. But this molecule right here is really, really, really high in potential energy. It took a lot of energy to get those phosphates to come together. As a matter of fact, that wasn't just going to happen. And if I wanted that to happen randomly, I would have to jack the temperature up really high. So if I want to supply energy to something, I can basically give a GTP to it, or a molecule that you've probably heard of before called ATP. That's why ATP is called the high energy molecule. It's because it's got those 3 phosphates together. Now, I can also add this phosphate group to a sugar or something if I want to add energy to that sugar. Now, why would I want to do that? Well, in order to get a reaction, you often have to give it a little bit of energy to start. So, for example, if I want to light gasoline on fire, I can't just put it out in a cup. It won't light on fire. I have to apply some kind of spark to it. So that phosphate group can sometimes be that spark. And we're going to see that again. So the things I need you to remember about the phosphate group right now is that it's almost always going to be negatively charged, and that negative things repel each other. So to put 2 negative things together is going to mean that they are really, really hard to get together, and that molecule is going to be high in energy. And then if you think about it, a molecule like the one I'm about to pull up here, and I don't want to give it away before I pull it up. Bam. Alright, so this guy here, you know, it's got a ton of phosphates, right? And unfortunately I'm on a train, so I can't get the internet right now. But if I pulled up First Glance and highlighted phosphates, you would see that all these little green guys here are all negative. All negative. So one thing about DNA, and we take advantage of this all the time in the lab, is that if I put a plus sign like over here, and you know you've got the DNA right there, that DNA is going to come really close to the plus sign as much as it can. And you can actually pull DNA through like mesh, basically. And because we can do that, we actually can separate DNA based on sizes. And I'll explain that again later. So, again, phosphate group. It's going to be something involved in reactions because we know it adds energy to things. It's going to be very negatively charged, and it's going to be very hard to get 2 negatively charged things together. That's it for the phosphate group. I will see you guys most likely tomorrow. Bye.